Tomorrow, NASA opens the vault on the high-rise images they have been sitting on for over 40 days. Before you watch that carefully choreographed presentation, I need you to understand something about the game being played. Just weeks ago, during their Mars Biosignature press conference, NASA spent considerable energy establishing a narrative, a brand story about transparency and trustworthiness. They used specific language, repeated phrases, deliberate framing. And now, as we stand on the eve of what could be the most important astronomical revelation in human history, that same language is about to be deployed again. But here is what they are not telling you. The delay itself is the message, the curation is the answer, and the gap between what they say about openness and what they actually do with critical data tells you everything you need to know about what might be coming tomorrow. Before we dive deeper into this, I want to ask you something. If you find value in this kind of analysis, in connecting dots that mainstream coverage ignores, please take a moment to like this video and subscribe to the channel. It genuinely helps the algorithm understand that people want this level of investigation, and it ensures you will not miss what comes next. Tell me in the comments where you are listening from, what time it is in your part of the world, and most importantly, what you think NASA will actually reveal tomorrow. Will they show us everything, or will we get a sanitized version of reality? I'm genuinely curious about your thoughts. The transparency paradox. Let us start with what happened during the Mars press conference, because the parallels are impossible to ignore. Secretary Duffy opened the presentation by reminding everyone that for over 30 years, every single time NASA thought it detected signs of life, they put it out to the scientific community immediately. That was the phrasing, immediate release, pressure testing from peers, radical transparency. Nikki Fox doubled down with even more explicit language. The moment we found it, we put out the images for everybody to see and everybody to share. She was building a narrative about NASA as an institution that never sits on data, never delays, never filters. Think about the intentionality of that messaging. This was not casual conversation during a press briefing. This was scripted, rehearsed, coordinated communication strategy. They were establishing credibility in advance, creating a benchmark against which future actions would be measured. And then Fox delivered the line that matters most for what is about to happen tomorrow. We are ultra-transparent. If we had this exciting news and I did not bring it to you, you would go, "You're trying to hide stuff from us." That statement, on the record, defines what hiding looks like according to NASA's own standards. But here is where the paradox begins to reveal itself. Lindsay Hayes echoed the same messaging later in that same press conference. As Secretary Duffy said, we are trying to be very transparent. Originally announced, we found a signal. This paper is showing we understand the context. The formula was consistent throughout. Announce signal, publish context, brand it as transparency, control the narrative. Every spokesperson hit the same talking points with machine precision. We are going to be transparent. If we have exciting news, we are going to share it. We will continue to let you know what we find, what we see, what we think. Now put that rhetoric next to what actually happened with 3i Atlas and the high-rise images. NASA shot those images from Mars on the 2nd and 3rd days of October. The high-rise camera aboard the Mars Reconnaissance Orbiter captured side views of the interstellar object from a distance of 29 million kilometers, achieving a spatial resolution of 30 kilometers per pixel. That is 3 times better than what Hubble managed. These frames sat in NASA's system while the public was told essentially nothing beyond vague references to government shutdown and bureaucratic process. 43 days passed. 43 days where time-sensitive scientific data that could fundamentally alter our understanding of interstellar visitors, and potentially our place in the cosmos, was held hostage to politics and procedure. The images that could have informed additional observations, guided telescope time allocation, shaped international scientific coordination, all of it delayed. And during this delay, something interesting happened. Mainstream coverage began doing cleanup work before the official reveal. Articles started appearing with headlines suggesting that radiohydroxyl absorption confirms 3i. Atlas is a normal comet. Stories hyping best quality images while quietly assuring readers there is nothing alien here, nothing unusual, nothing to see. This is not reporting. This is narrative management. The message was being seeded into public consciousness before NASA even released the data. Frame it as normal, establish the interpretation in advance, so that when the images finally appear, people are already primed to accept the conventional explanation. It is a sophisticated form of expectation setting, and it works precisely because most people do not notice it happening. Compare that managed rollout to the behaviour of 3i Atlas itself. We have a sunward anti-tail that defies standard dust-tail physics. Jets firing both toward and away from the sun simultaneously. Chemistry that has been flagged as unusual in multiple independent observations. A trajectory along the ecliptic that has a statistical probability of 0.2%. An interstellar visitor the size of Manhattan, approaching the inner solar system with characteristics that do not match anything in the training dataset of traditional comet expertise. None of this fits the narrative of normal that is being constructed. So what should you actually expect from NASA's presentation tomorrow? Not raw data dumps, not unprocessed FITS files available immediately for independent analysis, not a frank admission of unresolved anomalies. What you should expect is a polished storyline. High-rise images shown in carefully processed form, optimized for public consumption rather than scientific investigation. A safe size range for the nucleus that fits within comfortable parameters. Reassurance that jets and anti-tail behavior, while interesting, can be explained by conventional outgassing models with perhaps some unusual surface topology or composition variables thrown in for flavor. The presentation will likely emphasize what the images show while carefully avoiding discussion of what they do not show. There will be computer-generated models demonstrating how a comet could theoretically produce the observed features under specific conditions. There will be references to ongoing analysis and additional observations needed. There will be the appearance of transparency while maintaining careful control over what information enters the public domain and in what form. Here is what to listen for tomorrow, because the gaps will tell you more than the statements. First, do they specify when the raw high-rise frames will be released in FITS format, not just pretty JPEGs for press releases, but actual scientific data that independent researchers can analyze? If they avoid that question or give vague timelines, that is meaningful. Second, do they acknowledge any unresolved features, asymmetries, or fragmentation that does not fit simple comet models? If everything is explained away neatly with no remaining mysteries, that should raise flags. Third, do they address the full list of anomalies that have been documented by multiple research teams, or do they cherry-pick the ones that are easiest to explain conventionally? Fourth, and this is crucial, pay attention to how they discuss the 40-day delay itself. Will they take ownership of the fact that political and bureaucratic considerations were prioritized over time-sensitive scientific data release? Will they acknowledge that this directly contradicts their own stated standards about immediate transparency? Or will it be glossed over, treated as an unfortunate but unavoidable circumstance, quickly moving past the uncomfortable questions about why data was held when the agency's own rhetoric demands immediate release? The Mars Biosignature press conference gave us the script. Ultra-transparent, we put out images for everybody to see. We are sharing it with you, the world. We will continue to let you know what we find, what we see, what we think. Those were NASA's own words, their own standard, their own promise. Tomorrow's presentation is where we find out if that standard applies equally, when the stakes are higher, when the object in question is not Martian microbes but an interstellar visitor exhibiting behavior that challenges fundamental assumptions. Think about what transparency actually means in this context. True transparency is not the same as communication. You can communicate extensively while being completely opaque. True transparency means making raw data available immediately, explaining delays when they occur, acknowledging uncertainties openly, and trusting the scientific community and public to handle complex information responsibly. It means not managing the narrative, not seeding interpretations before data release, not processing images in ways that might obscure features researchers want to examine independently. The government shutdown explanation deserves particular scrutiny. Yes, there was a shutdown. Yes, bureaucratic rules exist about data release during funding lapses. But those rules are not laws of physics. They are policy choices that can be overridden when scientific priorities demand it. When Congresswoman Anna Paulina Luna publicly called for the data release, when international scientific interest reached unprecedented levels, when the public fascination with 3i Atlas exceeded anything seen for previous astronomical objects, the decision to maintain the delay was exactly that, a decision. Not an inevitability, not a force of nature, but a choice about priorities, and that choice reveals something important. It reveals that, despite the rhetoric about putting science first, about immediate transparency, about sharing exciting discoveries with the world, there are other considerations at play. Approval processes, review chains, message coordination, making sure that when data does go public, it comes with the right framing, the right context, the right interpretation already attached. This is not malicious. It is institutional behaviour. But it is also not the ultra-transparency that was promised. Meanwhile, as NASA sat on the high-rise images, amateur astronomers and international space agencies continued making observations. China's Space Administration released images from their Tianwen-1 probe, lower resolution than high-rise, but available to researchers immediately. Civilian astrophotographers captured stunning detail of multiple jets, both sunward and anti-solar. Spectral analysis from backyard observatories revealed gasless spectra despite bright green emission. The scientific work continued around the delay, but it continued without the best data available, without the images that could have resolved key questions about nuclear structure, jet geometry and surface features. That is the real cost of the delay, and it is not measured in days or bureaucratic inconvenience. It is measured in lost opportunities for coordinated observation, for targeting additional instruments at specific features, for catching transient phenomena while they are still active. 3i Atlas is not waiting for NASA's approval process. It is evolving in real time, changing as it moves through space, and every day without the best available data is a day where critical information might be missed forever. Tomorrow's presentation will be professionally produced. The images will be spectacular. The explanations will be delivered by credentialed experts using appropriate scientific language. There will be graphics and animations and carefully prepared talking points. And all of that is fine. But remember, presentation is not the same as transparency. Polish is not the same as openness, and a well-managed reveal is not the same as immediate data sharing. So watch tomorrow with clear eyes, listen for what is said, but listen even harder for what is not said. Notice which questions get answered and which get deflected. Pay attention to whether raw data becomes available, or whether we get curated products. And most importantly, hold NASA to their own standard, the one they established during the Mars press conference. The one about ultra-transparency and immediate sharing and never hiding the ball. Because if 3i Atlas really is just an unusually large dirty snowball, with some interesting surface features, then there is no reason to delay, no reason to manage the message, no reason to carefully control the information flow. The data should speak for itself. But if there is something more complicated happening, something that challenges conventional models, something that might require the public and scientific community to grapple with genuinely anomalous observations, then suddenly the 40-day delay makes perfect sense. Not scientific sense, not transparency sense, but institutional management sense. The rhetoric meets reality tomorrow. We will see which one wins. 12 anomalies that break physics. Avi Loeb recently compiled a complete list of 12 distinct anomalies associated with 3i Atlas, and when you examine them together, something remarkable emerges. These are not minor deviations from expected behaviour. These are not things that can be explained by saying we need more data, or our models need refinement. These are fundamental violations of how natural comets behave, and the statistical improbability of all 12 occurring in a single object approaches numbers so small they become almost meaningless. Let us work through them methodically, because each one builds on the last, and by the time we reach 12, you will understand why conventional explanations start to fracture under the weight of accumulated evidence. Anomaly 1. The retrograde trajectory is aligned to within 5 degrees of the ecliptic plane. Now, comets from the Oort cloud, from interstellar space, from anywhere outside our solar system, they approach from random directions. 3-dimensional space is vast, and there is no preferred plane unless you are gravitationally bound to the solar system's formation disk. The probability of a truly random interstellar visitor happening to align this closely with the ecliptic? 0.2%. That is not impossible, but it is the first red flag, the first time you should pause and ask why. Anomaly 2 takes us to the sunward jet, the anti-tail that appeared in July, August and early November. We have discussed this before, but the specific physics matter here. When dust is pushed away from a comet by solar radiation pressure, it goes away from the sun. Always. The pressure from photons hitting dust particles creates a force vector pointed radially outward from the star. For material to move sunward toward the source of radiation pressure, you need a different mechanism entirely. You need momentum transfer in the opposite direction. You need something pushing material toward the sun with enough force to overcome radiation pressure. Natural sublimation of ice does not do this. The geometry does not work. Anomaly 3 is about mass and velocity together. The nucleus is approximately 1 million times more massive than Oumuamua and 1,000 times more massive than Comet Borisov, while simultaneously moving faster than both. Large objects moving at high interstellar velocities are statistically rare because of how gravity works during stellar encounters. The bigger something is, the more likely it gets captured or deflected by stellar gravity wells during its journey. Fast and massive together has a likelihood below 0.1% among interstellar objects we would expect to detect. Anomaly 4 gets fascinating because it involves fine-tuning of arrival time. The trajectory brought 3I Atlas within tens of millions of kilometers from Mars, Venus and Jupiter, while being completely unobservable from Earth during perihelion. Think about the geometry required for that. Solar system space is vast, planets are tiny targets, and the specific timing needed to pass near multiple planets while hiding behind the sun from Earth's perspective is extraordinarily precise. The calculated probability is 0.005%. That is 1 in 20,000. Not impossible, but when you start stacking these probabilities, multiplying them together, the compound improbability becomes staggering. Anomaly 5 brings us to chemistry, and this is where things get particularly strange. The gas plume contains significantly more nickel than iron. In natural cosmic chemistry, in stellar nucleosynthesis, iron and nickel are produced together in specific ratios. Type 1 supernovae create them in lockstep. Interstellar dust, primordial solar system material, it all has predictable iron to nickel ratios. But 3I Atlas shows nickel dominance without corresponding iron, similar to what you see in industrially produced nickel alloys here on Earth. The ratio to cyanide is orders of magnitude larger than any known comet, including Borisov. Probability of this occurring naturally? Below 1%. Anomaly 6 is the water problem. The gas plume contains only 4% water by mass. Water is the primary volatile in comets. It is what makes them comets rather than asteroids. When you heat a dirty snowball, you get water vapor first, massive amounts of it, because water ice has a low sublimation temperature and it dominates the composition. 4% water is not a comet in any conventional sense. It is something else with a small amount of water contamination, or surface frost, or trace amounts mixed into a primarily dry structure. That inverts the entire model. Anomaly 7 deals with polarization, with how light interacts with the material in the coma. 3I Atlas shows extreme negative polarization that is unprecedented for all known comets including Borisov. Light waves have orientation, and when they reflect off or scatter from particles, that orientation changes in predictable ways depending on particle size, composition, and structure. The polarization signature from 3I Atlas does not match comet dust. It does not match any natural cometary material in our database. Probability below 1%. Anomaly 8 connects to the WOW signal, that famous 1977 radio detection from the direction of Sagittarius. 3I Atlas arrived from a direction coincident with that signal to within 9 degrees. Now, this could absolutely be coincidence. 9 degrees is not pinpoint precision, but it is another datum point, another improbability to add to the stack. 0.6% chance of random alignment. Individually dismissible, but in combination with everything else, it becomes part of a larger pattern. Anomaly 9 happened near perihelion. The object brightened faster than any known comet and became bluer than the sun. Comets typically get redder as they heat up because thermal emission shifts toward longer wavelengths and dust dominates the scattered light. Blue emission requires either extremely fine dust with Rayleigh's scattering properties or something emitting in blue wavelengths directly. The rate of brightening exceeded all models for how sublimation should increase with solar heating. The temperature curve, the luminosity curve, they did not follow the expected physics. Anomaly 10 is about the geometry of jets and the energy budget required to produce them. The sunward and anti-solar jets require an unreasonably large surface area to absorb enough sunlight to sublimate enough ice to feed the observed mass flux. When you calculate the energy needed, when you work through the thermodynamics of ice sublimation and gas expansion, the numbers do not close. Either the surface area is enormous, much larger than the nucleus size estimates suggest, or the mechanism producing the jets is not sublimation at all. There is an energy mismatch, a budget shortfall that cannot be reconciled with standard comet physics. Anomaly 11 focuses on non-gravitational acceleration. Near perihelion, the object exhibited trajectory changes that require evaporation of at least 13% of its total mass. 13%. When something loses 13% of its mass explosively near the Sun, it breaks up. It fragments. It shows visible disruption. Preliminary imaging indicates 3I Atlas maintained structural integrity. It did not break apart. So where did the mass go that would be needed to produce the observed acceleration? How do you shed 13% of your mass without visible fragmentation? This is not a minor discrepancy. This is a fundamental contradiction between the observed acceleration and the observed structural stability. Anomaly 12 is perhaps the most subtle, but also the most telling. The tightly collimated jets maintain orientation across 1 million kilometers in multiple directions relative to the Sun despite measured rotation. When a comet rotates, its jets rotate with it. The active areas on the surface, the spots where sublimation is most intense, they move as the nucleus spins, and the jets sweep across space like lighthouse beams. But 3I Atlas shows jets that hold their orientation, that remain pointed in specific directions even as the object tumbles. That requires either an incredibly slow rotation period, rotation rates that would be unusual for something this size, or it requires active orientation, some mechanism that adjusts jet direction to compensate for rotation. Neither explanation is comfortable. Now let us step back and look at what we have built here. 12 independent anomalies, each one with a probability ranging from a few percent down to a few hundredths of a percent. When you multiply probabilities of independent events, you multiply the individual chances. 0.2% times 5 thousandths of the 1% times 1% times 1%. The compound probability drops into the territory that is effectively zero. Not mathematically zero, but so improbable that it challenges the assumption that these are actually independent random occurrences. This is where conventional science reaches an uncomfortable point. You can explain any single anomaly. You can construct scenarios where trajectory alignment happens by chance, where nickel dominance comes from an unusual parent body composition, where low water content results from extended interstellar irradiation. But explaining all 12 simultaneously requires increasingly contrived scenarios stacked on top of each other. At some point, Occam's razor starts cutting in an unexpected direction. The alternative hypothesis, the one that makes many scientists deeply uncomfortable, is that some of these anomalies are not independent. That there is a common cause, a single explanation that accounts for multiple observations simultaneously. And when you start looking for common causes that could produce trajectory fine-tuning, chemical anomalies, jet directionality, structural integrity under high acceleration, and precise geometric alignment, you end up considering possibilities that fall outside the natural formation and evolution category. What if the ecliptic alignment is not chance but targeting? What if the low water content is not depletion but design? What if the jets maintaining orientation despite rotation is not unusual physics but active control? These questions sound like science fiction, and perhaps they are. Perhaps there are natural explanations we have not considered yet, exotic comet formation scenarios in unusual stellar environments that produce exactly this combination of features. But the intellectual honesty required here means acknowledging that artificial origin constructed object deliberate trajectory. These hypotheses are not less probable than 12 independent natural anomalies all occurring in the same object by chance. The training data set problem Loeb frequently mentions becomes relevant here. Comet experts have studied solar system comets for decades. Their understanding is built on observations of icy bodies formed 4.5 billion years ago in our Sun's protoplanetary disk. When they see 3I Atlas, they filter it through that training data. They try to fit it into existing categories because that is how expertise works. You pattern match against known examples, but humanity has launched technological objects into space. We have sent probes beyond the solar system. The Tesla Roadster from the Falcon Heavy launch is currently on a heliocentric orbit that will eventually take it into interstellar space. In billions of years, if it survives, it will be an interstellar object, an artifact, human-made, travelling between stars. When it eventually enters another star system, will astronomers there recognise it as artificial? Or will they try to classify it as an unusual asteroid, puzzling over its anomalous composition and geometric features? The point is not that 3I Atlas must be artificial. The point is that artificial should be in the hypothesis space being considered, tested with the same rigour as natural explanations. If we remove artificial from consideration a priori, if we decide in advance that interstellar artifacts are so improbable we will not seriously entertain the possibility, then we guarantee we'll never recognise one even if it passes right through our solar system. These 12 anomalies are not proof. They are not smoking guns. They are data points that collectively suggest something unusual is happening, something that deserves investigation without preconceived conclusions. Tomorrow's high-rise images might resolve some of these anomalies. They might show surface features that explain the jet geometry or structural details that account for the mass budget or evidence of fragmentation that was not visible at lower resolution. Or they might add a 13th anomaly to the list. And at some point, the stack gets too high to ignore. The ghost shell mystery. While professional observatories debated nomenclature and bureaucrats delayed data releases, amateur astronomers were making discoveries that should not exist. Perfect circular shells expanding around the nucleus, detached rings floating, in space like smoke rings frozen in time. Structures that violate everything we understand about how cometary material disperses into the vacuum of space. The first detection came from routine monitoring images, a faint ring, almost imperceptible, floating around 3I Atlas at a distance that seemed impossibly organised. On the 9th day of November, the ring measured 1.2 arc minutes in diameter. 4 days later, on the 13th, it had grown to 1.4 arc minutes. That is 20% expansion in 4 days. But here's what makes it extraordinary. The ring remained circular, perfectly circular. Think about what happens when you release gas and dust into space from a rotating, irregularly shaped nucleus. The material expands outward, but not uniformly. Faster jets in some directions, slower seepage in others. The rotation of the nucleus causes the ejection sites to sweep around, creating spiral patterns, twisted filaments, asymmetric lobes. What you absolutely do not get is a perfect circle expanding at a constant rate while maintaining geometric precision. Yet that is exactly what multiple observers documented. The ghost shell, as it became known in amateur astronomy forums, behaved like an expanding bubble from a single point source release. But 3I Atlas is not a point source. It is kilometres across with complex surface topology, multiple active regions, jets firing in different directions, all while rotating. The math does not work for a natural dispersion pattern to maintain circular symmetry. Then came the detached shell's discovery. And this is where the situation moved from puzzling to genuinely anomalous. 5 separate rings, concentric but not touching, spread across 150,000 kilometres of space around the nucleus. Not shells in the sense of continuous surfaces, but ring structures with discrete boundaries, each one maintaining its form as it drifted outward from the central object. 150,000 kilometres is roughly 40% of the distance from Earth to the Moon. These structures span a volume of space larger than many planetary systems. And they are organised. They have spacing. They have regularity. Natural dust and gas dispersion does not do this. When comets release material, it forms a coma, a fuzzy cloud with density gradients. It does not organise itself into distinct, separated ring structures with measurable gaps between them. The imaging that captured these shells came from backyard setups. We are talking about amateur astrophotographers using consumer-grade equipment, cooled cameras, modest aperture telescopes, tracking mounts you can buy commercially. Yet they were seeing structure that professional surveys missed, or at least did not report. Why? Because professionals are often looking for specific things, running automated detection algorithms optimized for point sources or diffuse nebulosity. Unusual geometric structures can slip through those filters, dismissed as artifacts or instrumental effects. But when multiple independent observers using different equipment, different cameras, different optical configurations all start reporting the same structures, artifact explanations become strained. Instrumental effects do not correlate across different instruments. Processing artifacts do not appear in raw, unprocessed frames from multiple sources. What you are left with is the uncomfortable conclusion that the structures are real, they are there in space around 3I Atlas, and they demand explanation. Several hypotheses emerged to account for the shells. The first, most conservative, suggested that discrete ejection events separated in time could produce expanding shells that remain separated as they move outward. If 3I Atlas had 5 major outbursts, each one releasing material in a roughly spherical pattern, those shells would expand at slightly different velocities depending on ejection force, and they would remain distinct in space. This works mathematically, but it requires very specific conditions. The ejections need to be isotropic, releasing material equally in all directions. That is not how jets work. Jets are directional, collimated, asymmetric. To get spherical shells from jets, you would need the nucleus to be rotating fast enough during the ejection event that jets sweep across all directions, averaging out to spherical over the duration of the burst. But we have measurements suggesting relatively slow rotation, and we have observations of jets maintaining orientation. The isotropic ejection scenario has problems. The second hypothesis involved interaction with the solar wind. Perhaps material released from 3I Atlas gets caught by solar wind plasma, organized by magnetic fields, shaped into ring structures by magneto-hydrodynamic effects, as it expands away from the nucleus. The solar wind does have structure, it does have magnetic fields embedded in it, and those fields can influence the motion of charged particles and dust grains. But here is the issue. Solar wind pressure is weak. It can push material over long distances and long time scales, but shaping discrete ring structures requires forces strong enough to overcome the initial velocity dispersion of the ejector, and the rings would need to maintain their structure despite differential solar wind pressure at different distances from the Sun, despite the Parker spiral structure of the interplanetary magnetic field, despite the time-varying nature of solar activity. It is possible, but it requires a very delicate balance of forces. The third hypothesis is more speculative but addresses some of the geometric precision issues. What if the shells are not expanding material but standing wave patterns? What if material released from 3I Atlas interacts with something, creates oscillations, and those oscillations manifest as density variations that appear as rings when we observe them, standing? Waves require boundary conditions, reflecting surfaces or resonant cavities. In empty space you do not naturally get those conditions, but if 3I Atlas has a magnetosphere, if it is somehow generating magnetic fields that interact with ionized material in the coma, you could potentially set up wave patterns that organize dust and gas into structured forms. This gets highly speculative quickly because natural comets do not have magnetospheres. They do not generate magnetic fields strong enough to shape their comae. You would need dynamo action, rotating conductors, electrical coil currents flowing through the nucleus, all of which requires mechanisms that do not exist in standard comet models. The amateur observers who discovered these structures are not wild-eyed conspiracy theorists. They are serious astrophotographers with decades of experience imaging comets, asteroids, deep sky objects. They know what artifacts look like. They know how to calibrate their equipment, how to process data properly, how to distinguish real structure from noise. When they report something unusual, it warrants attention. One particularly detailed analysis used multiple nights of imaging to create time-lapse sequences showing how the ghost shell expanded. Frame by frame, night after night, the ring grew outward while maintaining its circular form. The expansion velocity was calculated at approximately 500 meters per second, which is consistent with dust and gas moving away from a comet under low-pressure release. but the uniformity of that expansion, the lack of any asymmetry or distortion as the material travelled tens of thousands of kilometres from the nucleus, that remains unexplained. Another observer noted something subtle but potentially significant. The rings appeared to have slight variations in brightness around their circumference, but those variations were not random. They had structure, patterns that repeated at specific angular positions, as if the rings had preferred directions, orientations aligned with something. Solar wind direction was one possibility. The ecliptic plane orientation was another. But the data was not conclusive enough to determine what the alignment was pointing toward. The detached shells also raised questions about mass budget. If 3i Atlas released enough material to create 5 distinct shells each, spanning thousands of kilometres, and containing enough dust to be visible from Earth, that represents a substantial fraction of the total Comet mass. Where did all that material come from? Is the nucleus actively eroding, shedding layers like an onion? Or is material being recycled somehow, released and reabsorbed in cycles that we do not fully understand? Professional astronomers reached out to some of the amateur observers, requesting raw data files, imaging parameters, calibration details. Some collaboration happened, some data was shared. But the mainstream coverage of 3i Atlas rarely mentioned the shells. They focused on the bright nucleus, the jets, the spectroscopic measurements. The weird geometric structures documented by amateurs did not fit the narrative being constructed, so they were quietly omitted from most press releases and scientific summaries. This is not unusual in astronomy. Amateur discoveries often take time to be validated and incorporated into professional literature. There is a natural skepticism, a need for verification, confirmation from multiple independent sources using different methods. But when time is limited, when an object is moving through the inner solar system, and will soon be too far away for detailed observation, delays in validating amateur findings mean those findings might never get the scrutiny they deserve. The ghost shell mystery connects to something deeper about how we study transient phenomena. 3i Atlas is not a static object sitting in one place waiting for us to examine it carefully. It is moving, evolving, changing as it interacts with solar radiation and the interplanetary environment. Features that are visible today might be gone tomorrow. Structures that form near perihelion might dissipate as the object moves outward. We have one chance to observe this passage, and if we miss something, because we are waiting for proper validation channels, for peer review, for official confirmation, then we miss it permanently. The shells might be visible in the high-rise images. If NASA captured 3i Atlas at the right time or with the right exposure settings, those detached rings should show up as faint halos around the central brightness of the nucleus and inner coma. Or they might not be visible if high-rise was optimized for nucleus detail rather than extended structure. Orbital cameras have limited dynamic range. You expose for the bright nucleus and you blow out the faint extended features. You expose for the faint halos and the nucleus becomes a saturated blob. You cannot always get both. What the amateur observations prove beyond doubt is that 3i Atlas has complexity we are only beginning to recognize. The more carefully people look, the more structure emerges. And when that structure includes geometric precision, circular symmetry, organized ring systems, all the things that natural dispersion processes do not easily produce, you have to start asking uncomfortable questions about what mechanisms are operating here. Are we looking at physics we do not understand? Processes that happen in interstellar space, in primordial material exposed to cosmic rays for billions of years, that produce unexpected behavior when heated by a star? Or are we looking at something engineered? Structures that maintain form because they were designed to maintain form? Geometry that is precise because precision is built into the system? The shells are still there, still expanding, still visible to anyone with decent equipment and clear skies. They are not going away. They are evidence waiting to be properly investigated, properly explained, properly integrated into our understanding of what 3i Atlas actually is. Spectroscopy's impossible result. A civilian researcher using an 80mm refractor, a Star Analyzer 100 grating, and a cooled monochrome camera just produced what might be the most important data point we have on 3i Atlas. The spectrum was extracted with custom Python code, processed carefully to remove contamination, calibrated against known standards. The wavelength range covered 628 to 808 nanometers, the far red edge of visible light bleeding into near-infrared. And when the analysis was complete, when the spectral lines were identified and catalogued, the result was impossible. 30 spectral peaks, not a single one belonging to gas. Let me be very clear about what this means. 3I Atlas has a bright green coma. It has massive jets visible in imaging from multiple observers. It is actively releasing material that forms structures tens of thousands of kilometers across. Every piece of visual evidence says this object is outgassing violently. But the spectrum, the light broken down into its component wavelengths, shows no CN, no C2, no CO+, no water bands, nothing. The spectral signature of an object that should be screaming with cometary gases is completely silent. The green emission is particularly problematic. In every comet ever studied, green colour comes from diatomic carbon, C2 molecules, fluorescing under solar ultraviolet radiation. The swan bands, as they are called, produce distinct emission lines in the green part of the spectrum. They are so reliable, so universal in comets, that green coma is essentially synonymous with C2 emission, except 3I Atlas shows green without C2. The coma is glowing, the colour is there in every photograph, but the spectral signature that must be causing that colour is absent. Several explanations were considered immediately. Perhaps the spectral resolution was insufficient. Perhaps the 80mm aperture and consumer-grade grating simply could not detect faint emission lines that a professional spectrograph would reveal. But the spectrum was not noisy. It was clean, well-calibrated, with 30 distinct peaks that were clearly identified. If C2 emission was present at levels strong enough to produce visible green colour, it would be detected. The sensitivity threshold was well below what would be needed. Perhaps the wavelength range missed the relevant emission lines. C2 has strong bands around 516 nanometers in the green part of the visible spectrum. The civilian observation covered 628 to 808 nanometers, which is redder than the main C2 features. But water has bands in that range. CN has features there. Other common cometary species have infrared signatures that should have appeared. The spectrum showed none of them. Perhaps the observation caught 3I Atlas during a quiet period. A lull in activity when jets had temporarily shut down and gas emission dropped below detection limits. But imaging from the same time period showed active jets. The coma was bright. Material was clearly being released. The timing argument does not work when simultaneous observations in different wavelengths show completely contradictory things. What the spectrum does show is dust. 30 peaks identified as continuum features, thermal emission from solid particles heated by sunlight. The spectral slope is red, consistent with the old irradiated material. The temperature estimates derived from the continuum fit suggest they are dust grains in thermal equilibrium with solar radiation at that distance. This all matches previous findings from professional observatories. Southern Astrophysical Research Telescope confirmed red slope. Putzier and colleagues found no volatiles before perihelion. Jewett and Liu noted the same absence. Everyone agrees 3I Atlas is red, dusty, and chemically quiet in wavelengths that should be showing gas emission. But red dusty objects do not have bright green comae. They do not produce massive jets. They do not exhibit the visual appearance of active comets while simultaneously showing dust-only spectra. This is the contradiction that breaks standard interpretation. Either the green colour is not coming from gas emission, which violates basic cometary physics, or gas emission is happening, but producing spectral signatures we cannot detect with current methods, which suggests exotic chemistry or plasma physics beyond normal comet behaviour. The featureless spectrum has another implication that makes many researchers uncomfortable. A smooth continuum with no emission or absorption lines is exactly what you would expect from reflected sunlight off a surface. Metal, rock, processed minerals, they all produce relatively featureless spectra if the surface is smooth or covered with fine dust. Spectroscopy fundamentally cannot distinguish between ancient natural dust and metallic engineered surfaces coated with dust. Both would show red continuum, both would lack gas features, both would appear thermally consistent with solar heating. This does not prove artificial origin, but it means spectroscopy cannot rule it out. We cannot point to the spectrum and say, obviously natural because of these spectral signatures, when the signatures are absent. The data is neutral on the question of composition beyond confirming that dust dominates and gas is not detected. The intermittent jet behaviour compounds the mystery. On the 15th of November, 3I Atlas looked calm. Green coma, no visible jets. Then on the 16th, jets returned at full strength, large symmetric plumes both sunward and antisolar. Natural comets do not behave this way. Jets correlate with solar heating. As a comet rotates, different parts of the surface face the sun, and jets activate and deactivate with rotation period. But the active regions do not completely shut off for a day and then reappear at full power 24 hours later. That requires either an implausibly slow rotation period, rotation rates measured in days rather than hours, or it requires something controlling jet activity independent of solar heating. The combination of gasless spectrum and intermittent jets suggests something very specific about the mechanism producing visible activity. If sublimation of ice is not driving the jets, what is? Several exotic possibilities exist. Dust jets without significant gas are theoretically possible if you have fine particles being lifted electrostatically or through mechanical disruption rather than gas pressure. But dust-only jets have slow acceleration. They lack the collimation and intensity seen in 3I Atlas jets, and that they still should produce some gas signal as surface frost sublimates. Plasma effects offer another avenue. If 3I Atlas has electrical potential, if it is charging up as it moves through the solar wind and then discharging periodically, those discharges could accelerate dust and ions into jet-like structures. The green emission could come from plasma fluorescence rather than molecular emission. Ionized material emits light at specific wavelengths determined by temperature and density, and some plasma conditions produce greenish glows. But natural objects do not charge up to discharge potentials high enough to create plasma jets. You need very specific electrical environments, active current generation, mechanisms that again do not exist in standard comet models. Another consideration is that the spectral coverage might be missing critical diagnostic lines. If 3I Atlas is releasing unusual molecules, exotic chemistry from interstellar processing, those molecules might emit at wavelengths outside the observed range. Ultraviolet spectroscopy would reveal different species. Far infrared would show thermal emission from complex organics. The visible to near infrared range that was observed is just one window, and conclusions drawn from limited wavelength coverage might miss the full picture. Professional observatories with better equipment, wider wavelength coverage, higher spectral resolution, they could potentially resolve these questions, but time on those instruments is limited. Proposal cycles are long, and 3I Atlas is moving away from optimal observing geometry. The window for detailed spectroscopy is closing. If the observations are not made soon, if the necessary data is not collected while the object is still accessible, we will be left with partial information and unresolved mysteries. The civilian observation has value precisely because it happened. While professional astronomers wrote proposals and waited for telescope time, while committees reviewed and scheduled and allocated, an individual with modest equipment took the initiative to collect data. The result is not publication quality by journal standards, but it is real information about a real object at a specific time, and the information contradicts expectations in fundamental ways. This is where citizen science proves its worth, not because amateurs replace professionals, but because they fill gaps. They observe when official channels are slow, they try things that might not pass formal proposal review. Sometimes those efforts produce artifacts and noise. Sometimes they produce genuine discoveries that professional astronomy might have missed. The spectral mystery connects directly to the question of what 3I Atlas is made of. If it is a water-rich comet like solar system comets, it should show water bands. If it is a carbon-rich object, it should show carbon emission lines explaining the green colour. If it is primordial material from the early universe or the outer reaches of a different stellar system, it should show chemistry that reflects that origin. What it actually shows is dust and nothing else in the observed wavelength range, which is consistent with multiple scenarios, but definitive about none. One interpretation that deserves consideration is that 3I Atlas is exactly what some researchers suggested early on. A primordial object, ancient dust aggregated in interstellar space, or in the outer disk of a long-dead star system, irradiated for billions of years by cosmic rays and interstellar radiation. That would produce a red featureless spectrum. It would explain the lack of volatiles. It might account for the dust-dominated composition, but it leaves the jets unexplained. It does not address the green coma, and it cannot account for the geometric precision in shell structures or the orientation maintenance of collimated plumes. Another interpretation starts from the opposite direction. If you wanted to design an interstellar probe that would survive billions of years in transit through hostile space, you would coat it in dust. You would use radiation shielding, ablative layers, material that can handle cosmic ray impacts and micrometeorite erosion. That probe would arrive at a destination looking like a dust-covered rock. Its spectrum would be featureless, dominated by whatever material you used for shielding. And if it activated near perihelion, if systems came online that used stored volatiles or electric propulsion, or any mechanism beyond passive sublimation, the resulting jets might not correlate with standard cometary gas emission. These interpretations are speculative, but they illustrate the range of possibilities left open by the spectral data. We cannot conclusively say natural origin based on the spectrum, because the spectrum does not show what natural comets show. We cannot conclusively say artificial origin because dust spectra are ambiguous. What we can say definitively is that 3I Atlas is anomalous, its spectroscopic properties do not match its visible behaviour, and current models do not adequately explain the discrepancy. The researcher who conducted this analysis published the findings on social media with full methodology, raw data access, processing scripts, open science, transparent methods, inviting verification and critique. That openness stands in stark contrast to the 40-day delay on professional high-rise images, the controlled narrative, the managed information flow. When amateurs practice better transparency than official agencies, that says something about where we are in this investigation. Tomorrow's high-rise release will not include spectroscopy. Orbital cameras take pictures, not spectra. But if the images show surface features, if they reveal composition through colour variations or reflectance properties, that data combined with spectroscopic measurements could start resolving some of these questions, or it could deepen the mystery further, adding visual evidence of structures that make even less sense given the gasless spectrum. The impossible result stands: green coma with no gas, jets with no volatiles, activity with no spectroscopic signature of the processes that should be driving that activity. 30 peaks telling us what is there, dust, while the absence of peaks tells us what is not there, everything else we expected. Jets that obey no rules. The jets from 3I Atlas violate thermodynamics in ways that become more obvious the longer you examine them. Not small violations, not subtle discrepancies that could be explained by the measurement uncertainty or modelling assumptions. Fundamental violations of energy conservation, momentum transfer, and the basic physics of how gases expand into vacuum. Start with the energy budget problem. When ice sublimates, it absorbs energy. That energy comes from sunlight heating the surface. You can calculate exactly how much energy hits a given surface area at a given distance from the sun, account for albedo and surface properties, and determine how much ice can sublimate per second. This is not complex physics. It is thermodynamics 101, textbook material covered in undergraduate courses. For 3I Atlas at perihelion distance, the solar flux was intense, enough energy to sublimate significant amounts of water ice if water ice was present on the surface. But the jets we observe, the mass flux moving through those collimated plumes, requires sublimation rates that exceed what the available surface area can provide. Even if you assume 100% efficiency, even if every photon hitting the surface goes into sublimating ice with no losses to thermal radiation or conduction, the numbers do not close. The surface area needed to feed the observed jets is larger than reasonable size estimates for the nucleus. Several factors compound this problem. First, jets are not isotropic. They do not release material uniformly in all directions. They are collimated, focused into more narrow beams. That collimation requires force asymmetries, pressure gradients, mechanisms that direct material preferentially rather than letting it expand spherically. In normal comets, collimation comes from subsurface cavities, gas venting through cracks, geometric focusing by topographic features. But that level of collimation typically occurs at smaller scales, individual vents a few meters across producing jets a few degrees wide. 3I Atlas shows collimation maintained across thousands of kilometers, jet widths that remain narrow, even as the plume extends vast distances from the nucleus. Second, the jets maintain directionality despite rotation. We have measurements indicating 3I Atlas rotates. The light curve shows periodic variations, but the jets, particularly the sunward anti-tail and the long collimated tail extending away from the sun, they do not sweep around. They hold orientation. For a rotating body, maintaining fixed jet direction requires one of two scenarios. Either the rotation axis is aligned exactly with the jet axis, so rotation does not change the jet's orientation relative to the sun, or the active regions producing jets are somehow compensating for rotation, adjusting their output to keep the jet pointed in a specific direction as the nucleus spins. The first scenario is geometrically unlikely. Rotation axes can point anywhere. The probability that a random rotation axis aligns closely enough with both a sunward direction and an anti-solar direction to explain both jets is small, and it does not help with the multiple other jets observed at various angles. The second scenario requires mechanism we do not have. Natural outgassing does not adjust its direction based on rotation. It comes from wherever the ice is exposed and heated. If that region is rotating into and out of sunlight, the jet turns on and off with rotation period. It does not hold a constant orientation in space independent of rotation. That would require active nozzle vectoring, thrust directional control, systems that sense orientation and adjust output accordingly. Then there is the intermittent behavior. Jets appearing at full strength, disappearing completely, reappearing 24 hours later. This cycle happened multiple times during observations. Natural sublimation driven by solar heating does not work this way. When a comet approaches the sun, heating increases, sublimation increases, jets get stronger. When it moves away, the process reverses. But there is no mechanism in passive ice sublimation that causes complete shutdown and restart on day timescales while solar distance is barely changing. You could propose that the active regions are on a surface that rotates into shadow, blocking solar heating and shutting down the jets until the region rotates back into sunlight. But the rotation period would have to match the observed on-off cycle, and it would have to be a very specific geometric configuration where the active regions are concentrated on one hemisphere. Most comets have multiple active regions distributed across the surface, producing jets that overlap and blend into continuous activity, even if individual vents turn on and off. The sunward jets present their own unique problem. Dust and gas pushed by radiation pressure move away from the sun. To move sunward, toward the source of radiation pressure, requires momentum in the opposite direction. Something must be pushing material sunward with enough force to overcome not just radiation pressure, but also the initial velocity dispersion of the ejector. In some comets, you see apparent anti-tails that are actually optical illusions, geometric projections where tail material sweeping through the orbital plane appears to point sunward from certain viewing angles. But those have been ruled out for 3I Atlas through careful geometric analysis from multiple observation points. True sunward material motion requires a force directed toward the sun. Electric fields could do this if the nucleus is negatively charged and the sun's electric field pulls ions inward. But electric forces strong enough to overcome radiation pressure on dust particles require very high charge densities, potential differences measured in kilovolts, electrical environments that natural objects do not spontaneously generate. You need active charge separation, current generation, dynamo mechanisms. Gravitational focusing is another possibility. If material is released from the far side of the nucleus, it orbits around under the nucleus's gravity and can appear to come from the sunward direction. But 3I Atlas is small, only kilometers across, with negligible gravity. Escape velocity is measured in meters per second. Typical gas velocities from sublimation are hundreds of meters per second. Material would not be gravitationally bound. It would fly off in straight lines, not orbit around to create focused beams. The mass loss problem adds another layer of impossibility. Calculations based on non-gravitational acceleration indicate at least 13% mass loss near perihelion. That is not a small number. Losing 13% of your mass is catastrophic for structural integrity. Comets that lose that much material fragment, they break apart. We see this regularly in sun-grazing comets, objects that pass too close to the sun and disintegrate from thermal stress and mass loss. Yet 3I Atlas maintained integrity through perihelion, emerged on the other side with no visible fragmentation, no debris field, no indication of structural failure. Where did the mass go? If 13% mass loss had occurred through gas and dust ejection, we should see that material in the coma. In tail structures, in the brightness and extent of observable features, the dust production rate should be enormous. Yet observations show a relatively modest coma, jets that are impressive but not unprecedented, no massive expanding debris cloud that would indicate bulk mass ejection. Perhaps the calculation is wrong, perhaps the gravitational acceleration can be explained by smaller mass loss combined with highly directional ejection that provides more thrust per unit mass. Rocket equation mathematics say you can get more velocity change from collimated ejection than from isotropic outgassing. But even accounting for directional efficiency, the numbers remain uncomfortable. Either we are missing material, or the acceleration is being produced by mechanisms other than mass ejection. All of these issues compound together. It is not just one thing wrong, it is thermodynamics and directionality, and timing and mass budget all simultaneously inconsistent with natural cometary activity driven by solar heating of water ice. You can handwave one or two anomalies by appealing to unusual conditions or extreme parameter values, but explaining all of them requires increasingly contrived scenarios. What if 3I Atlas is not primarily water ice? What if it is mostly dry material with small volatile reservoirs that activate intermittently? That could explain the low water content in spectroscopy, the unusual chemistry, perhaps even some of the jet timing. But dry material does not produce bright comae. It does not create massive plumes, and it does not explain directionality or the energy budget issues. What if the jets are not sublimation driven at all? What if material is being released through mechanical processes, electrostatic lofting, explosive decomposition of complex organics, any mechanism that does not rely on simple ice turning to gas? Some of those mechanisms exist in nature. Dust devils on Mars are electrically driven. Impact processes can explosively release material. Stored energy in metastable chemical compounds can provide thrust, but none of those mechanisms naturally produce the organized, sustained directional jet activity observed here. The conversation keeps circling back to control systems, not necessarily intelligent control, but any mechanism that regulates output based on conditions rather than responding passively to solar heating. Humans build machines with directional thrusters, intermittent activation, planned thrust sequences. Those are engineered solutions to propulsion problems. Could natural processes produce similar results? Is there some exotic comet formation environment where geological processes create structures that function like nozzles and valves even though they form naturally? It is possible. Unlikely distributions of unlikely properties sometimes happen. But at what point does unlikely become implausible? At what point do you start assigning higher probability to explanations that involve design rather than explanations requiring multiple independent, extremely low probability natural phenomena all occurring in the same object? The jets continue their enigmatic behavior even as 3I Atlas moves outward from perihelion. Some observers report continued activity. Others note decreasing brightness suggesting jets are weakening. Monitoring continues, imaging continues, spectroscopy continues. Each observation adds data points, but so far the data points are not converging on a coherent natural explanation. Tomorrow's high-rise images might show something definitive. Surface vents in specific configurations, topographic features that explain collimation, evidence of fractured regions where subsurface volatiles could be exposed, visual confirmation of mechanisms that reconcile the observed jet properties with known physics. That would be the best outcome, the resolution that lets everyone breathe easier and go back to thinking of 3I Atlas as an unusual but natural interstellar comet. Or the images might show a smooth featureless surface with no obvious source regions for the jets, uniform coating with no vents, no cracks, no topographic variation that explains directional activity. That outcome would intensify questions rather than answer them, would push the mystery deeper into uncomfortable territory where standard explanations no longer suffice. The jets know what they are. The physics operating here is consistent, reproducible, producing effects we can measure and document. Our understanding is incomplete, our models are inadequate, and our assumptions about what is possible for a natural object might need fundamental revision to accommodate what 3I Atlas is demonstrating. The Pleiades revelation. While 3I Atlas dominates discussions of unusual objects in our immediate vicinity, another discovery reshapes how we understand stellar families and ancient structures across the galaxy. The Pleiades, the 7 sisters you can see with naked eyes on clear nights, are not 7 stars. They are not even the few hundred stars that telescopes revealed over the past century. The Pleiades are the bright core of a structure containing over 3,000 stars spanning 2,000 light-years of space, 20 times larger than anyone suspected. This matters for 3I Atlas because it illustrates how profoundly we can misunderstand even the most familiar objects when we lack the right tools or perspectives. The Pleiades have been observed for as long as humans have looked up. Ancient texts mention them. Indigenous cultures across the planet incorporate them into creation myths and calendars. The Greeks named them the 7 Sisters. Japanese culture represents them in the Subaru logo. These are not obscure distant galaxies requiring billion-dollar telescopes to study. These are naked-eye stars everyone can see, yet we were wrong about their fundamental nature by a factor of 20. The discovery came from combining data sources in novel ways. NASA's Transiting Exoplanet Survey satellite, designed to hunt planets, was repurposed to measure stellar rotation rates. Those rotation measurements served as a cosmic clock because stars spin down as they age. Young stars rotate rapidly, angular momentum gradually dissipating over millions of years. By measuring rotation, researchers can determine age. And when thousands of stars scattered across hundreds of light years all show the same ages to high precision, that tells you something important. They were born together. The European Space Agency's Gaia spacecraft provided the second critical dataset. Gaia maps stellar positions and motions with extraordinary precision, tracking how stars move through the galaxy. When you know where stars are now and how they are moving, you can calculate where they were in the past. Rewind the motion, trace trajectories backward, and see if they converge on a common origin point. For the Pleiades, that convergence happened 100 million years ago, when the entire extended family was concentrated in a single massive star-forming region. Chemical analysis from the Sloan Digital Sky Survey added the third confirmation. Stars born together from the same molecular cloud have similar elemental abundances because they formed from the same material. Different regions of the galaxy have different compositions, enriched by different supernovae, processed through different stellar generations. Chemical fingerprints are like DNA for stars, traceable markers of common ancestry. The extended Pleiades show consistent chemistry across the entire 2,000 light-year structure, proof they share origins despite their current dispersion. This three-pronged approach, rotation age, kinematic traceback, chemical tagging, creates a framework for identifying stellar families even after they have dissolved and scattered. Most star clusters do not remain gravitationally bound. Over hundreds of millions of years, they disperse into the general galactic population. What looks like isolated field stars might actually be siblings separated by vast distances, still carrying signatures of their shared birth, but lost in the stellar crowd. The new methodology reveals those hidden relationships. The implications ripple outward. If the Pleiades are 20 times larger than traditional observations suggested, how many other stellar structures have we fundamentally misidentified? How many apparent clusters are actually just the dense cores of sprawling associations we have not recognized? How much of the stellar population near the Sun is organized into extended families rather than random distributions? This connects to 3I Atlas through the question of origin. Where did it come from? Not just what stellar system, but what kind of system? A single isolated star, a binary, a dense cluster where planetary systems might be disrupted by gravitational interactions. Understanding stellar environments matters when you try to reconstruct the history of an interstellar visitor. If 3I Atlas originated in a cluster similar to the Pleiades, it experienced very different conditions during formation than if it came from a sparse region of space. The age timeline is particularly relevant. The Pleiades are 100 to 150 million years old, young by galactic standards, still in the early phases of evolution, where the brightest stars are massive blue giants burning through their fuel rapidly. In a few 100 million years, those massive stars will explode as supernovae, enriching the local environment with heavy elements and potentially disrupting any remaining gravitational structure. Star clusters have lifespans, formation to dissolution, measured in hundreds of millions to billions of years depending on density and environment. 3I Atlas, by contrast, is estimated to be billions of years old based on surface irradiation indicators. It has been travelling through interstellar space, exposed to cosmic rays and background radiation for an enormous span of time. The Pleiades did not exist when 3I Atlas began its journey. The Sun itself was younger. Most of the stars currently visible in Earth's night sky were in different positions or had not yet formed. This is ancient material, carrying information about the galaxy. As it was in arrears, we can only study through indirect evidence. The discovery of extended stellar structures also raises questions about how common such organisation is. Are most stars born in clusters that eventually disperse? Is the Sun part of an extended family we have not recognised yet? Using the same techniques applied to the Pleiades, rotation measurements and kinematic tracing and chemical analysis, researchers could potentially identify the Sun's siblings, stars formed in the same nebula 4.5 billion years ago, but now scattered across the galaxy. That search has begun, but finding ancient dispersed siblings is harder than finding young ones like the Pleiades. Rotation rates converge over time. Old stars of similar mass rotate at similar speeds regardless of age, making rotation clocking less effective for old populations. Kinematic traceback becomes increasingly uncertain over billions of years as the galaxy rotates and gravitational interactions scramble trajectories. Chemical signatures remain useful but require high-precision spectroscopy to distinguish subtle variations. The challenges are significant but not insurmountable. If the Sun has siblings, if we can identify them and study their planetary systems, that provides comparative data for understanding solar system formation. Did other stars from the same nebula form similar planetary architectures? Do they have asteroid belts at comparable distances? Did they experience similar dynamical evolution? These questions connect to understanding how typical or unusual our solar system is, which in turn informs estimates about planetary systems around other stars, including the systems that might have produced 3I Atlas. The Pleiades revelation also demonstrates how technology opens new observational windows. TESS was designed for exoplanet transits. Its data on stellar rotation was a secondary product, not the primary science goal. Gaia was built for the astrometry, precise position measurements, to create the most accurate three-dimensional map of the galaxy ever made. Chemical surveys like Sloan were mapping galactic composition for various astrophysical studies. None of these instruments were specifically designed to find extended stellar families, yet combining their data produced exactly that discovery. The right question applied to existing data revealed something hidden in plain sight. This suggests similar revelations might be waiting in other datasets. Telescopes observe the sky constantly, accumulating data on millions of objects. Most of that data gets analysed for its primary scientific purpose and then archived. But archived data retains value for questions that were not even being asked when it was collected. Someone with a new hypothesis, a different analytical approach, a novel combination of data sets, can mine archives and discover things the original observers never saw. 3I Atlas might benefit from this archival approach. Have previous sky surveys captured images of it before it was recognised as interstellar? Do photographic plates from decades ago show precursor objects in similar orbits? Could we reconstruct where it was 1,000 years ago, 10,000 years ago, by searching historical records for unusual observations that might match its predicted past positions? These are long shots, but long shots occasionally succeed, and the payoff for finding additional data points would be substantial. The scale shift from 7 stars to 3,000, from a compact cluster to a 2,000 light-year structure, forces a psychological adjustment. What we think we know about familiar objects might be incomplete, might be based on limited perspectives or inadequate tools. The bright stars we see are real, but they are just the most visible part of a larger reality that extends far beyond what casual observation reveals. You need specific instruments, specific analyses, specific questions to see the full picture. 3i Atlas is visible. Telescopes can image it. Spectroscopy can analyse its light. But are we seeing the full picture? Is what appears in visible light just the bright core of something more extensive? The ghost shells and detached rings suggest there is structure we are only beginning to recognise. The spectral mysteries indicate composition we do not fully understand. The jet behaviour implies processes we cannot yet model. Like the Pleiades before the recent revelation, we might be looking at a bright familiar object while missing the larger context that explains what it actually is. The search for stellar siblings continues. The Greater Pleiades complex is now mapped, its extent documented, its member stars catalogued. Other clusters will receive similar treatment. Other stellar families will be reconstructed from scattered remnants. Our understanding of galactic structure is shifting from isolated stars and discrete clusters to a more nuanced picture of interconnected families, dispersed associations, extended networks that span vast volumes of space. And somewhere in that vast network, in some stellar system we might never identify, around some star that might not even exist anymore, 3i Atlas was formed. It carries information about that origin, chemical signatures, structural properties, maybe even records, if it is artificial, of the civilization that created it. Finding those clues requires looking beyond surface appearances, combining multiple data sources, asking questions that do not fit standard frameworks. The Pleiades taught us that lesson. 3i Atlas might teach us even more profound ones about what can exist between stars and what can survive the enormous spans of time and distance that interstellar travel requires. When stars destroy worlds, 40 light-years from Earth, a red dwarf star just demonstrated why the search for habitable planets might be more complicated than we hoped. Astronomers detected the first confirmed coronal mass ejection from a star beyond our Sun, and it was violent enough to strip the atmosphere from any planet unfortunate enough to be in its path. This is not theoretical extrapolation from solar behaviour. This is direct observation of a stellar explosion that travelled at 5.4 million miles per hour, dense enough and energetic enough to destroy worlds. The detection came from combining radio observations with X-ray measurements, a multi-wavelength approach that captured both the initial eruption and the resulting shock wave as it propagated through the star's corona and into interplanetary space. The radio signal was the key, a characteristic burst called a Type II radio emission that occurs when a fast-moving shock creates plasma instabilities. That signature is unique to coronal mass ejections, distinct from other stellar activity, impossible to mistake for anything else. The star itself is nothing like our Sun. It is a red dwarf, roughly half the mass, much cooler, much dimmer, but also far more active Sol. It rotates 20 times faster than the Sun, generating a magnetic field 300 times more powerful through dynamo processes driven by that rapid rotation. The stellar surface is covered with massive star spots, dark magnetic regions where field lines pierce through and create active zones. When those field lines become too twisted, too stressed, they snap and reconfigure, releasing enormous amounts of stored magnetic energy in the process. That is what a coronal mass ejection is, fundamentally. Magnetic energy converted to kinetic energy, plasma accelerated to extreme velocities and flung into space. On the Sun, we see this regularly. Solar CMEs drive space weather, create aurora when they hit Earth's magnetosphere, occasionally disrupt power grids and satellite systems when they... But the Sun's CMEs are gentle compared to what this red dwarf produced. The observed event was in the top fraction of 1% of solar CMEs in terms of speed and density, a rare extreme outlier if it had occurred on our star. But here is the critical point. This is not an outlier for the red dwarf. This appears to be normal activity for this type of star. Red dwarfs are magnetically hyperactive, especially young ones that still rotate rapidly. They flare constantly, release CMEs frequently, bombard their surroundings with radiation and energetic particles at levels that would sterilize Earth's surface if our Sun behaved similarly. And red dwarfs are the most common type of star in the galaxy. comprising roughly 70% of all stars in the Milky Way. Most of the potentially habitable exoplanets discovered so far orbit red dwarfs. The reason is observational bias combined with planetary architecture. Red dwarfs are dim, so their habitable zones, the regions where liquid water could exist on a planet's surface, are much closer to the star than Earth is to the Sun. Planets orbiting close to dim stars are easier to detect through both transit methods and radial velocity measurements. They block more light during transits because the star is smaller, and they pull harder on the star gravitationally because they orbit closer. Detection techniques favour finding planets around red dwarfs, but habitability is not just about temperature and liquid water. It is about whether a planet can maintain an atmosphere over billions of years. And when your host star is firing atmosphere-stripping CMEs at you regularly, when energetic radiation is bombarding the upper atmosphere and driving hydrodynamic escape, when stellar wind is eroding the magnetic field that would otherwise protect the surface, maintaining habitability becomes profoundly challenging. The detected CME from this red dwarf travelled at 2,400 km per second. That velocity is sufficient to cross the star-planet distance for a close orbiting world in hours, not days. The planet has no warning, no time to prepare, assuming preparation were even possible for a geological system. The shock hits, compresses the magnetosphere if one exists, channels particles into polar regions, heats the upper atmosphere to escape temperatures, and drives mass loss. Do that repeatedly over millions of years, and you lose the atmosphere entirely, leaving a barren, rocky surface exposed directly to stellar wind and radiation. Some planets might survive. If they have strong intrinsic magnetic fields, robust magnetospheres that can deflect most of the CME impact, they could potentially retain atmospheres even under heavy bombardment. Earth has benefited from its magnetic field, generated by dynamo action in the liquid iron outer core. Mars lost its magnetic field early, and subsequently lost most of its atmosphere to solar wind stripping. The difference between a habitable world and a dead rock can come down to whether the planetary interior maintains the convection patterns needed to generate protective magnetic fields. But generating strong magnetic fields requires specific conditions. The planet needs to be large enough to have retained significant internal heat. It needs a liquid conducting layer undergoing vigorous convection. It needs rotation fast enough to organise that convection into dynamo action. Small planets cool quickly, solidifying their interiors and shutting down magnetic field generation. Tidal locking, which often occurs for close orbiting planets around red dwarfs, can slow rotation to match orbital period, potentially affecting dynamo efficiency. The requirements for magnetic protection are not trivially met. The observation raises uncomfortable questions about biosignature searches. Telescopes currently being designed, like the Habitable Worlds Observatory, will look for atmospheric signatures that might indicate life. Oxygen, methane, combinations of gases that are out of thermodynamic equilibrium and thus suggest biological production. But if planets around red dwarfs, which are most of the targets for these searches, cannot maintain atmospheres because of CME bombardment, then the biosignature search becomes significantly more constrained. You're looking for life around stars that actively prevent life from establishing. This does not mean all hope is lost. Perhaps life adapts. Perhaps subsurface oceans remain habitable even when surfaces are sterilized. Perhaps early origin of life occurs during brief windows when the host star is less active before settling into hyperactive phases. Perhaps we should focus searches on older red dwarfs that have spun down, rotating slower, generating weaker magnetic fields, producing fewer extreme CMEs. But it does mean the simple calculation of habitable zone boundaries and planetary detection rates does not translate directly into habitable world counts. The environmental hostility matters. The detection method is as important as the result. Combining radio and X-ray observations, using data from both the Low-Frequency Array Radio Telescope LOFAR and the European Space Agency's XMM Newton X-ray Observatory, provided complementary views of the same event. LOFAR caught the radio burst from the shockwave. XMM Newton measured the X-ray emission from the hot plasma. Together, they confirmed what was happening unambiguously. Single wavelength observations can be ambiguous. Artifacts or instrument effects might mimic real signals. multi-wavelength confirmation eliminates most uncertainty. This technique can now be applied systematically. LOFAR is operational, continuously monitoring the sky at radio frequencies. XMM Newton is available for targeted observations. Other red dwarfs can be studied, looking for similar events. Over time, a statistical understanding will emerge. How often do red dwarfs launch atmosphere-destroying CMEs? Does frequency depend on age, rotation rate, stellar mass? Are there safe red dwarfs, old quiet ones that no longer threaten their planets, where biosignature searches make more sense? The timing is interesting given 3I Atlas discussions. Here we have a hostile universe perspective, stars that destroy rather than nurture, cosmic environments that prevent life from establishing or maintaining. It is a reminder that space is not benign. Radiation, impacts, extreme temperatures, vacuum, all of these factors challenge habitability. Life on Earth survives in a narrow envelope of conditions protected by atmosphere, magnetic field, distance from the sun, stable climate maintained by the complex feedback systems. Remove any of those protections, and habitability vanishes quickly. 3I Atlas travelled through that hostile environment for billions of years. Interstellar space is cold, nearly absolute zero. Cosmic rays bombard anything exposed. Interstellar dust grains impact at hypervelocity. There is no star providing warmth, no planets to interact with gravitationally, no structure or organisation beyond the object itself. Whatever 3I Atlas is, it survived that journey intact enough to arrive here exhibiting active behaviour. That speaks to either extraordinary durability of natural materials or deliberate engineering for survival. Natural objects can be durable. Rocks survive. Metallic asteroids remain solid. Ice protected by an insulating dust layer can persist for enormous time spans. But maintaining complex and internal structure, retaining volatiles, preserving mechanisms that can activate after billions of years dormant, these are more challenging requirements. Most materials degrade, radiation damage accumulates. Thermal cycling from occasional star encounters causes expansion and contraction that fractures structure. You would not expect a loose rubble pile to hold together, or a delicate icy matrix to remain functional. The CME observation provides a calibration point for understanding stellar environments, the conditions that planets must withstand if they are going to host life. By extension, it informs thinking about what conditions an artificial probe would need to withstand during interstellar travel. If you're designing something to survive the journey from one star system to another, what engineering challenges do you face? Radiation shielding is essential. Micrometeorite protection is necessary. Thermal management to handle the cold of deep space and the heat near stars is critical. Energy storage or generation for systems that need to function after millions of years. Structural integrity under acceleration and impact. Navigation and course correction capabilities. Those engineering requirements translate into observable properties. A shielded object looks different from an unshielded one. A power generation system produces waste heat. Navigation requires sensors and thrusters. All of these leave signatures that could potentially be detected if you know what to look for and if the object exhibits those behaviours. 3I Atlas has shown unusual properties that might, if interpreted through an engineering lens rather than a purely natural lens, align with some of these requirements. Thermal behaviour that does not match pure ice. Directional activity that resembles thrust. Structural integrity through high-stress events. The red dwarf CME detection will not resolve questions about 3I Atlas, but it enriches the context. It shows that the galaxy contains destructive forces on scales that challenge habitability. It demonstrates that observational techniques can detect phenomena previously only inferred. It confirms that multi-wavelength approaches reveal things single-wavelength observations miss. And it reminds us that survival in space, whether for natural objects or artificial ones, requires robustness against environments that are fundamentally hostile. Tomorrow's high-rise reveal might show how 3I Atlas survived its journey, what its surface looks like after billions of years of interstellar exposure, whether there are features suggesting protective layers or dimage patterns or structural organisation, or it might show a nondescript rock, unremarkable except for its origin and behaviour, leaving us with more questions about how something so ordinary looking can behave so extraordinarily. Statistical impossibilities stack up. Numbers do not lie, but they can be deeply uncomfortable. When you start multiplying probabilities, when you calculate the compound likelihood of multiple independent improbable events all occurring together, you reach values so small they challenge intuition. This is where 3i Atlas pushes beyond unusual into territory that demands explanation. Because the stack of statistical improbabilities is not just high, it is approaching infinitesimal. Let us work through the mathematics carefully. Each anomaly has a probability, a calculated chance of occurring naturally, based on what we know about comets, stellar dynamics, interstellar populations, and observational statistics. Some probabilities are relatively benign, a few percent. Others are more extreme, fractions of a percent. When events are independent, when one occurring does not influence whether another occurs, you calculate compound probability by multiplication. Start with trajectory alignment to the ecliptic, 0.2%, which is 0.002 in decimal notation. Interstellar space is three-dimensional. Objects approach from random directions unless something constrains them. The ecliptic plane is a special reference related to solar system formation, meaningful for planets but arbitrary for interstellar visitors. Getting within 5 degrees of that plane by chance happens 2 times in 1,000. Not impossible, but notable. Next add arrival timing. 0.005%, which is 0.00005. The specific geometry required to pass near Mars, Venus and Jupiter while being unobservable from Earth during perihelion is extraordinarily precise. Solar. System space is vast. The inner planets occupy tiny regions of that space at any given time. Threading the needle to pass near multiple planets requires not just correct trajectory but correct timing. Being behind the Sun from Earth's perspective during closest approach adds another layer of geometric precision. 1 in 20,000 chance. Multiply these two. 0.002 times 0.00005 equals 0.0000001. That is 1 in 100 million just from trajectory and timing. We have not even considered chemistry or jet behavior yet. Add nickel dominance without corresponding iron. Below 1% probability. The ratios produced by stellar nucleosynthesis are well established. Type 1a supernovae create iron and nickel together in specific proportions. Cosmic abundances reflect those production mechanisms. Finding high nickel with low iron is unusual enough to suggest either very specialized formation environments or processing that separates elements, neither of which is common for cometary material. Call it 0.5% to be conservative. Multiply into the compound probability. 1 in 100 million times 0.005 equals 5 in 10 billion, or 0.000000005, 5 chances in 10 billion. At extreme negative polarization, below 1%, similar to the nickel anomaly. Polarization depends on particle size distribution, composition, and surface properties. The specific polarization signature from 3i Atlas does not match any natural cometary material in our database, including other interstellar comets. It is an outlier among outliers. Compound probability now drops to 5 in 1 trillion, 0.000000005. That is the current accumulation, and we have only included 4 of the 12 anomalies. We have not touched jets, water content, rotation, brightening behavior, mass loss, or any of the other documented oddities. The remaining anomalies have similar or smaller individual probabilities. Low water content defies the definition of what makes something a comet. Unusual brightening curve and a blue colour near perihelion contradicts thermal models. Non-gravitational acceleration without visible fragmentation violates structural mechanics. Jets maintaining orientation despite rotation requires geometric alignments or active control. Each of these adds another small probability factor into the multiplication. By the time you include all 12 anomalies, you are approaching probabilities measured in quintillions, sextillions, numbers so large they lose intuitive meaning. The compound chance of all 12 occurring together in a single object by pure independent random chance is effectively zero. Not mathematically zero, not impossible, but so improbable that it becomes intellectually dishonest to claim this is just bad luck, just an unusual comet that happens to violate expectations in every measurable way. This is where Bayesian reasoning becomes relevant. Bayesian statistics is about updating beliefs based on evidence. You start with prior probabilities, your initial assessment of how likely different hypotheses are before considering new data. Then you incorporate evidence, calculate likelihoods, and derive posterior probabilities that reflect updated belief given what you have observed. For 3i Atlas, the prior for natural comet might start high because most objects in space are natural. But as evidence accumulates, as each new anomaly emerges, the posterior probability shifts. The natural hypothesis does not get eliminated, but it becomes increasingly strained. You can maintain it only by accepting that an extraordinary collection of individually improbable features all happen to occur together, which itself requires explanation. The alternative hypothesis, artificial origin, might start with a very low prior, because interstellar probes are speculative, unproven, outside the normal range of astronomical objects. But artificial explains multiple anomalies with a single cause. Trajectory fine-tuning is expected if the object is targeted. Low water content makes sense for a probe that does not rely on ice reserves. Unusual chemistry could reflect engineered materials. Jets maintaining orientation suggests propulsion systems. Structural integrity under high acceleration is an engineering requirement for any craft. From a pure Bayesian perspective, if artificial provides a better fit to the data with fewer assumptions than natural, and if the compound improbability of natural becomes sufficiently extreme, then posterior probability shifts toward artificial, even if the prior was very low. This is not proof. Bayesian reasoning does not prove hypotheses. It quantifies relative plausibility given available evidence. The statistical argument becomes more compelling when you consider what we would expect to see if artificial probes are common in the galaxy. Enrico Fermi famously asked, "Where is everybody?" If intelligent civilizations exist elsewhere, if some are much older than humanity, and have had billions of years to spread through the galaxy, why do we not see obvious evidence of their presence? The Fermi paradox has many proposed resolutions, but one possibility is that we have not been looking correctly, that we expect extraterrestrial intelligence to look or behave in specific ways and miss evidence that does not fit those expectations. An interstellar probe would not announce itself. If it is a reconnaissance mission, if the purpose is observation without interference, it would look as natural as possible. It would not broadcast radio signals. It would not have flashing lights. It would pass through the solar system disguised as a comet or asteroid, collect data, and continue on to the next target system. Detecting such an object would require recognizing that its behavior deviates from natural expectations in subtle but measurable ways. 3i Atlas deviates from natural expectations in not subtle ways. The deviations are blatant, documented by multiple research teams, confirmed through independent observations. If we designed an interstellar probe and wanted it to be detectable by civilizations with technology comparable to ours, we would make it exhibit anomalies similar to what 3i Atlas shows: trajectory precision to ensure detection, unusual with chemistry to flag attention, jets that do not quite match natural cometary activity, enough signal to be interesting without being undeniable. This suggests a disturbing possibility. Perhaps 3i Atlas is designed to be ambiguous. Perhaps the anomalies are intentional, meant to make some fraction of observers question whether this is natural, while leaving enough uncertainty that it can be dismissed as unusual but not artificial. Why would anyone design ambiguous evidence? Because unambiguous first contact might be destabilizing, might trigger social or political reactions that are unpredictable. Ambiguity allows civilizations to discover the possibility of extraterrestrial intelligence at their own pace, lets them debate and consider and gradually accept before facing undeniable proof. If that hypothesis sounds like science fiction, consider that it is exactly what human planners would do if we sent probes to other star systems. We would design them to be ambiguous for any observers at our development level, or lower, obvious only to observers significantly more advanced. It is the ethical approach to first contact, minimizing cultural disruption while providing evidence for those ready to see it. The statistical stack does not prove this interpretation, but it makes it plausible. When natural explanations require compound improbabilities in the quintillions, when artificial provides a coherent single cause for multiple anomalies, Whether the design choices that would make sense for an intentionally ambiguous probe match what we observe, Bayesian reasoning shifts probability in uncomfortable directions. Critics will argue that extraordinary claims require extraordinary evidence. That is a valid principle. Claiming 3i Atlas is artificial is an extraordinary claim by any measure, but the evidence is not ordinary. 12 documented anomalies, each one improbable, all occurring in a single object, with compound statistics approaching impossibility. At what point does the accumulation of ordinary improbabilities constitute extraordinary evidence? At what threshold do we admit that natural explanations have been stretched beyond credibility? The intellectual honest position is not to declare certainty either way. It is to acknowledge that we do not know, that current data allows multiple interpretations, and that both natural and artificial hypotheses deserve serious consideration. Natural should not be assumed by default simply because it is familiar. Artificial should not be dismissed by default simply because it is unprecedented. Both should be tested against evidence, evaluated for explanatory power, assessed for consistency with observations. Tomorrow's high-rise images will not resolve the statistical questions. Images cannot measure probabilities, but they might provide new data points that either strengthen natural explanations by showing these features that account for anomalies, or weaken them by revealing additional unexplained characteristics. Each new observation shifts the Bayesian calculation, updates posteriors, moves us incrementally toward better understanding. The stack stands regardless of what images show. 12 anomalies with extreme compound improbability. That is the reality we need to explain. And explanations that require believing in quintillion to one coincidences might be less reasonable than explanations that require reconsidering assumptions about what can exist between the stars. What the images won't show. Tomorrow's presentation will be carefully designed. The images will be processed to highlight specific features, optimized for public consumption, presented with context and interpretation. What you will not see is raw data immediately available for independent analysis. What you will not hear is frank discussion of unresolved anomalies. What you will not get is admission that standard models fail to explain what 3i Atlas is doing. Understanding what is absent from the presentation is as important as understanding what is present. Start with image processing. When HiRISE captures images, it produces FITS files, flexible image transport system format used throughout astronomy for storing data with full calibration information. FITS files are not pretty. They are not ready for press releases. They contain raw pixel values, instrument response characteristics, exposure parameters, everything needed for scientific analysis. Converting FITS to pretty pictures requires choices about brightness scaling, contrast enhancement, color mapping if multiple filters are combined, noise reduction, artifact removal. Each choice affects what features are emphasized or suppressed. For public presentation, NASA will show processed images optimized to display the nucleus clearly. That processing typically includes logarithmic brightness scaling to handle the enormous dynamic range between the bright nucleus and faint extended features. It includes smoothing to reduce noise. It might include unsharp masking to enhance edge details. All of these are legitimate processing techniques used routinely in astronomical imaging, but there are also choices that affect interpretation. Logarithmic scaling compresses brightness differences. Features that are 10 times brighter and features that are 100 times brighter both appear relatively bright, losing the quantitative information about how much brighter one is than the other. That matters when you are trying to understand energy, distribution, mass distribution, activity patterns. Seeing that something is bright is different from measuring how bright it is relative to other features. Smoothing removes noise but also removes fine structure. If there are small scale features on the surface, jets a few pixels wide, asymmetries in coma brightness, smoothing might blend them into the background. The decision of how much smoothing to apply balances, noise reduction against feature preservation, and different analysts might make different choices based on what they are trying to emphasize. Unsharp masking enhances edges by subtracting a blurred version of the image from the original, making transitions sharper and making boundaries more visible. It is excellent for highlighting structure, but it can also create artifacts, apparent features that are products of the processing rather than real structure in the object. Distinguishing real from artifact requires examining unprocessed data, something the public typically does not get to do. The images will show the nucleus and inner coma because that is what HiRISE was pointed at and optimized to capture. Extended features like the ghost shells, the detached rings, the distant jet structures, those might not be visible because they are too faint, too diffuse, outside the field of view, or saturated out by the brightness of the nucleus. Orbital cameras have limits. You cannot image everything simultaneously with equal quality. Color information will be limited or absent. HiRISE primarily images in visible wavelengths, but detailed color analysis requires multiple filters, multiple exposures, careful calibration. If only one or two filters were used, color determination is ambiguous. The green that everyone sees in ground-based imaging might not appear in HiRISE data if the filters do not cover that wavelength range, or if exposure times were optimized for other purposes. Surface features, if visible, will be subject to interpretation. Is that depression a crater? Is that bright spot exposed ice? Is that linear feature a crack? Images alone do not tell you composition or structure. They tell you brightness variations and shapes. Interpretation requires models, assumptions about what kinds of processes create what kinds of features. Different researchers applying different models to the same images can reach different conclusions. Size estimates will come with error bars. Measuring the nucleus diameter from images requires determining where the nucleus ends and the coma begins. That boundary is not sharp. There is a gradient from bright center to diffuse outer region. Where you place the cutoff affects the size measurement. Different analysis techniques, different brightness thresholds, different assumptions about coma contribution all produce different size estimates. The quoted diameter will have uncertainty, probably tens of %, meaning an object described as 7 kilometers across might be 5 or might be 9. The presentation will likely include modeling results. Computer simulations showing how a comet could produce the observed features under certain assumptions. These models are valuable. They test whether proposed mechanisms are physically plausible. But models are only as good as their assumptions. If you assume sublimation-driven jets, the model will explore different sublimation scenarios. If you do not include alternative mechanisms, electromagnetic effects or explosive decompression, or active systems, the model will not explore those possibilities even if they better fit observations. Peer review and scientific consensus will be mentioned. The importance of careful analysis, the need for additional observations, all of which is true and appropriate, but it also serves to defer difficult questions. When something does not fit current understanding, the standard response is we need more data, we need more time, we need further study. That is reasonable scientific caution. It is also a way to avoid confronting the possibility that current understanding is wrong. Specific anomalies might be addressed individually. The sunward jets could be explained as geometric projections that are not actually moving toward the sun. The nickel emission could be attributed to unusual parent body composition. The low water content could result from extended irradiation depleting volatiles. Each explanation taken alone might sound plausible, but taken together as a package of explanations that all need to be true simultaneously, the combined scenario becomes strained. What you will not hear is acknowledgement of the compound improbability problem. The presentation will not say we have 12 independent anomalies each, with probability below 1%, and the chance of all 12 occurring together is so small we should seriously consider alternative hypotheses. That kind of statement would be scientifically controversial, would invite criticism, would position NASA as endorsing speculative interpretations. The safe approach is to present data, explain individual features conventionally, and avoid drawing conclusions that challenge paradigms. Press questions will be screened. Not all reporters will get to ask questions. The ones who do will likely focus on predetermined topics, size estimates, trajectory predictions, mission plans. Questions about artificial origin, about why the data was delayed 40 days, about what specific features would constitute evidence for non-natural processes, those might not get asked or might get deflected with references to ongoing analysis. The timing of the release is itself informative. If this were a normal scientific result, it would go through standard publication channels: data collection, analysis, manuscript preparation, peer review, journal publication. That process takes months or years. By releasing preliminary results in a press conference before formal publication, NASA is responding to public pressure, congressional interest, unprecedented attention. The presentation is as much about public relations as science. That does not make it dishonest, but it does mean the priorities are mixed. Satisfying public curiosity is a goal. Demonstrating transparency after criticism about delays is a goal. Maintaining scientific credibility is a goal. Avoiding controversy that might affect funding or mission approval is a goal. All of these compete with the goal of simply presenting data as neutrally as possible and letting observers draw their own conclusions. Watch for language choices. If the presentation describes 3I Atlas as a comet without qualification, that is framing. Comets are natural icy bodies. Calling something comet asserts its nature before proving it. More neutral language would be interstellar object, visitor, or even 3I Atlas without category labels. How speakers refer to the object reveals their assumptions. Watch for what gets emphasized versus what gets mentioned briefly. If jet geometry is discussed extensively but water content is mentioned once in passing, that tells you where the focus is directed. If surface features are shown in detail, but spectroscopic anomalies are referenced only generally, that prioritization suggests what NASA wants the narrative to be about. Watch for who is present. Are the speakers primarily NASA employees, or are independent researchers included? Are critics given voice, or is the panel unanimous in interpretation? Diversity of perspective in the presentation suggests openness to debate. Uniformity suggests message control. Listen for uncertainty language. Does the speaker say this is what we see, or this is what we think we see? Do they acknowledge alternative interpretations, or present one interpretation as if it were fact? Science operates on uncertainty, on probabilities and confidence levels. Presentations that erase uncertainty in favour of clean narratives are not doing science. They are doing communication, which is different. The images themselves will be fascinating regardless of interpretation. Seeing 3I Atlas at 30-kilometre resolution is unprecedented. Even if nothing unusual appears, even if it looks exactly like a normal comet nucleus should look, that is information. That tells us something about surface process, about how billions of years of interstellar travel affects appearance, about what survives the journey intact. If unusual features do appear, geometric patterns or surface organisation or anything that does not fit natural erosion and impact processes, that becomes a data point demanding explanation. But the images in the presentation will be selected, cropped, processed, annotated. The full data set, the complete collection of frames from multiple viewing angles at different times, that will not be available immediately. Researchers will request access. Proposals will be written. Data will eventually be released through formal channels. But the first look, the initial interpretation, the framing that shapes public understanding that happens tomorrow in a controlled environment designed to convey specific messages. Expect professionalism. Expect beautiful images. Expect explanations that sound reasonable. But also expect gaps, absences, deferred questions, and interpretations that serve institutional goals as much as scientific truth. And remember that what is not shown, what is not said, what is deflected or minimized, those absences contain information just as surely as the data that is presented explicitly. The question nobody wants to ask. If 3I Atlas were artificial, what would we expect to see? This is the question that makes scientists uncomfortable. The line of reasoning that feels like speculation rather than analysis. But it is a legitimate question, and answering it rigorously is the only way to determine whether observations are consistent with artificial origin or definitively rule it out. Avoiding the question because it seems fringe does not make it go away. It just means we explore possibilities poorly instead of exploring them well. Start with basic requirements for an interstellar probe. It needs to survive the journey, which means protection against radiation, micrometeorite impacts, and thermal extremes. It needs power, either stored energy sufficient for millions of years dormant plus active operations, or generation capacity like radioisotope systems or solar collection. It needs a propulsion for trajectory corrections, for orbital insertion, for maneuvering within the target system. It needs sensors to collect data, communication systems to transmit findings, processing capability to analyze and prioritize observations. And ideally it needs stealth, the ability to look natural to avoid alarming primitive civilizations that might react unpredictably to obvious artificial visitors. The shielding requirement explains several observed features immediately. A probe coated in dust covered with ablative material that has accumulated over billions of years in interstellar space would show a red featureless spectrum. Thermal emission from sun-heated dust would dominate. Any underlying structure, metal or composites or exotic materials, would be hidden beneath the coating. Spectroscopy could not distinguish this from a natural object because the outer layer is natural. Dust and ice and organic compounds swept up during the journey or deliberately applied as camouflage. The low water content makes sense for a probe that does not rely on water reserves. Why carry unnecessary mass? If propulsion uses stored gases or electric systems, if the only water is surface frost accumulated in transit, the overall water fraction would be much lower than a natural comet. When heated near the sun, that small water content might sublimate, but it would not produce the massive water vapor signature that dominates normal cometary activity. The unusual chemistry nickel dominance, without iron, could reflect engineered materials. Nickel alloys are used in aerospace applications because of favourable strength-to-weight ratios and corrosion resistance. A probe built with nickel-rich structural components experiencing surface erosion from the interstellar environment might release nickel atoms into the coma that get detected spectroscopically. The ratio to iron would not match natural cosmic abundances because the materials are not natural. They are chosen for engineering purposes. The jets become propulsion systems, directional thrust for trajectory maintenance, for slowing down after entering the solar system, for orbital adjustments to pass near multiple planets as observed. The intermittent behaviour is not mysterious if jets are active systems that fire on schedules or in response to commands. The orientation maintenance despite rotation is exactly what you would expect from gimbaled nozzles, thrust vectoring, systems designed to point in specific directions regardless of spacecraft attitude. The energy budget problem disappears if energy comes from internal sources rather than solar heating of ice. The trajectory fine-tuning is intentional targeting. An interstellar probe would not approach randomly. It would be aimed, would execute trajectory corrections during the final approach phase to ensure passage through regions of interest. Passing near Mars, Venus, Jupiter, while being hidden from Earth during perihelion, that is mission planning. That is deliberate geometry designed to observe multiple planets while minimizing detection risk during the most vulnerable phase, when solar heating might reveal structure, or when close observation from the target civilization is most likely. The arrival timing, the statistical improbability of everything aligning just right, is not improbability if it is designed. The compound statistics that seem impossibly small for natural occurrence become 100% for artificial design. Everything that appears anomalous under the natural hypothesis becomes expected under the artificial hypothesis. The structural integrity through high acceleration is engineering. Probes are built to withstand thrust loads, designed with margins for acceleration forces, tested to ensure components remain functional under stress. Natural objects fragment when acceleration forces exceed material strength. Artificial objects are specifically constructed to handle exactly those forces. The ghost shells and detached rings could be exhaust plumes, material ejected during propulsive burns and organizing into geometric patterns as it expands. The expansion rate matches what you would expect from expelled gas at several hundred meters per second, consistent with low-thrust chemical or electric propulsion. The circular symmetry suggests axial symmetry in the exhaust, which would be natural for a vehicle using rotational stability or symmetric thruster arrangement. The green emission, without corresponding C2 spectral lines, could be plasma from electric propulsion. Ion drives produce glows from excited gases that do not necessarily match thermal emission spectra. The colour depends on what propellant is used and what energy levels are achieved. Green or blue glows are common in certain electric propulsion systems, and the spectral signature would not show molecular emission bands because the emission comes from ionized atoms or from continuum processes rather than molecular fluorescence. Every major anomaly finds explanation under the artificial hypothesis, not just post hoc rationalization, not just making up stories to fit observations, but predictions that would have been made in advance if someone had asked what an interstellar probe should look like. The match is uncomfortably good, which is precisely why the question makes people uncomfortable. If observations fit artificial better than natural, that challenges fundamental assumptions about what we expect to find in space. But recognizing that artificial fits the data does not prove artificial. It establishes plausibility, nothing more. Other explanations might exist that fit equally well. Perhaps there are exotic natural processes we do not understand yet that produce the same observational signatures. Perhaps 3I Atlas is a freak occurrence, the one in quintillion natural object that happens to mimic artificial design. Low probability is not zero probability. The stronger argument comes from prediction. If 3I Atlas is artificial, what additional predictions can we make that would either confirm or refute the hypothesis? Artificial objects might show regularities in their behaviour, periodicities that reflect computational cycles or scheduled operations. They might exhibit learning, changing behaviour in response to observations of the environment. They might avoid certain actions that would risk discovery, like approaching too close to Earth or exhibiting obviously non-natural characteristics during high visibility phases. Some of these predictions are testable with continued observation. If jet activity follows precise schedules, if trajectory corrections happen at predictable times, if there are patterns in the intermittent behaviour that suggest control systems operating on algorithms. If the approach continues to avoid configurations that would allow detailed Earth-based observation, while favouring geometries that enable observation of other planets that suggests intentional manoeuvring. Other predictions might never be testable because a well-designed probe would avoid providing definitive evidence. If the purpose is reconnaissance without interference, revealing artificial origin defeats the mission. The probe should look as natural as possible while still accomplishing objectives. Only if something goes wrong, if systems malfunction, if the disguise fails, would undeniable artificial signatures appear. And even then, plausible deniability would be valuable, make it ambiguous enough that it can still be dismissed as unusual natural object by anyone who wants to maintain that interpretation. This raises the disturbing possibility that we might never know for certain. Even if 3I Atlas is artificial, even if it is an alien probe sent to study the solar system, the evidence might remain perpetually ambiguous. Enough anomalies to make some people question, but never enough to prove anything conclusively. And that ambiguity might be intentional, might be the ethical approach to first contact from an advanced civilization that wants to minimize cultural disruption. If you were designing first contact protocol, what would you do? Undeniable, obvious artificial objects, giant motherships appearing in orbit. That seems aggressive, threatening, likely to cause panic. Complete invisibility, perfect stealth, provides no benefit because the visited civilization learns nothing and has no opportunity to prepare for eventual contact. The middle ground is calibrated ambiguity. Make yourselves detectable to civilizations at a certain development threshold. Provide evidence that can be recognized by those ready to see it, but leave enough uncertainty that the discovery happens gradually, rather than as sudden shock. 3I Atlas fits that profile unsettlingly well. Obvious enough that scientists notice anomalies, ambiguous enough that consensus can be avoided, testable enough that investigation continues, subtle enough that public reaction remains muted because nothing is proven. If you wanted to introduce the concept of extraterrestrial technology slowly, letting humanity adjust to the possibility before facing reality, this is how you would do it. The question nobody wants to ask is actually the question everybody should be asking. Not because artificial origin is likely, not because we should abandon natural hypotheses, but because the question is scientifically tractable. We can list predictions, we can test them, we can compare how well different hypotheses account for observations, we can quantify relative plausibility using Bayesian reasoning and probability calculations. This is not speculation, this is methodology. Avoiding the question because it seems uncomfortable or fringe or outside mainstream science is not scientific thinking. It is social conformity, career protection, fear of ridicule. Real science asks whatever questions the data raises, tests whatever hypotheses might explain observations, and follows evidence wherever it leads, even if the destination is unexpected. Tomorrow's images will not answer the question. They might provide additional data that helps distinguish between hypotheses, but images alone cannot prove origin. What matters is that we ask the question openly, that we evaluate evidence honestly, and that we remain willing to revise our understanding if observations consistently point toward conclusions that challenge preconceptions. 3i Atlas has given us 12 anomalies, statistical improbabilities stacking toward impossibility, behaviour that matches artificial predictions as well as or better than natural models. That is not proof, but it is sufficient reason to take the question seriously, to investigate rigorously, and to acknowledge that the universe might contain surprises that exceed our current imagination. The question is on the table. What we do with it, how seriously we take it, whether we investigate or dismiss, that choice reveals more about us than about 3i Atlas. Are we ready to genuinely explore possibilities that make us uncomfortable? Or will we retreat to safe, familiar interpretations even when the evidence points elsewhere? Tomorrow begins to answer that question. Watch what gets said. Listen for what gets avoided. Notice whether the presentation engages with the full range of evidence or cherry-picks comfortable data. And decide for yourself whether the explanation you're given actually explains what you have observed, or whether it merely provides reassurance that nothing paradigm-shifting is happening. Because if something paradigm-shifting is happening, if 3i Atlas represents first detected evidence of extraterrestrial technology, then the paradigm will shift whether we are ready or not. The question is whether we shift with it, or spend years in denial before finally accepting what the data has been telling us all along.